So this is work I will present that is have been doing for the last almost 10 years. And it's basically started with a collaboration with Jaime Merino in Madrid. And then in Grenoble, Arnaud Ralco joined, and we have a PhD student working on this. And then for related aspects that I will not present here, also Vlad and other collaborators joined, and you will hear more about this later in this conference. So basically, we have been hearing already a lot about electronic correlations, which happen when you are either at half filling or integer filling or near half filling. What this talk is about is what happens when you have strong electronic interactions, but you are not at half filling, quite away from it. So electronic interactions can lead not only to correlations, but to charge order. And this already gives a lot of interest effects. But because we are not happy with only this, we also added one extra element, which is geometric frustration. And this happens when you try to stabilize the charge order on a triangular lattice. So I'll show you that all kinds of anomalous behaviors can come out of these ingredients. And hopefully at the end, I will convince you that there is one experimental system that shows some of these aspects and that can be described by the theory. So it all starts with this guy here. So it's back in the 30s. He was probably trying to understand why some materials are metallic, while some are insulating. And he realized that, by the way, this is Wigner. He realized that if there was no kinetic energy, then the only thing you want to do with electrons that are charged are arrange them in order to minimize their interaction energy. So this in 3D looks like a body-centered lattice. We are more interested here in two-dimensional materials. So in 2 dimensions, the ordering that you get is this triangular ordering. And why does this happen? Well, there is an average Coulomb interaction that, so Coulomb interaction scales like 1 over r. So on the average, if the particles are at the distance which you call rs, the Coulomb interaction energy is this E squared over rs. You can compare this now with typical kinetic energy, which is k squared over 2m. So kf will scale like 1 over the distance squared. And then you realize that if you are at very low density, so that the distance between particles is very large, then this term dominates, and you end up with some ordered state. So this is in the 30s. These ideas, well, actually, it was realized that they don't really apply in solids. And they were kind of replaced by something much more successful, which is the idea of a Mott transition. And this framework here applies to solids around integer filling. So the electron density is much higher than what Wigner was considering. So, well, we all know or imagine that this Mott physics is a very important problem, and it still gives rise to new discoveries, as Vlad was telling us today. Now, the question is there a relation between these two mechanisms? And can we find systems where they are both acting at the same time? And if you just observe that this happens at low density and this at a very high density of 1 particle per site, then the most natural place to look for this is to go somewhere in between. So somewhere in between, instead of going to 1/2 filling, so 1 particle per site, you can imagine going to systems where you have 1 particle per 2 sites. So this happens, it's quite common in 2-dimensional organics, as we will hear more in this conference. And in that case, the Hubbard model alone doesn't give you much because particles are too far apart and they don't see each other. So you have to add a term which at least, so you should add long-range interactions, but the minimal description is just nearest neighbor repulsion. So it's the next step after the Hubbard model. So when you do this, actually, you do get a combination of these two physics. So you get a charge ordering. So this is on a square lattice. You get this checkerboard ordering. I will mention again later. So you get charge ordering, but you still have a strong U, so you get correlation effects. And again, this is a competition between potential and kinetic energy, and the order happens typically when this V here is larger than some bandwidth-related scale. So this is more or less the framework for combining Wigner and Mott physics. Now I will add one more piece to the puzzle before I start really going to real materials, and it's frustration. So you have probably heard about magnetic frustration, which happens on geometrically frustrated lattices like the triangular lattice when you have antiferromagnetic interactions. So imagine you want to put two spins on a triangle. Well, you put one, the second one, you want to minimize the energy, so it will point opposite to the first one. And now when you put a third one, you're in trouble because you're happy with this one, but then these are pointing on the same direction, which gives a positive term to the energy. So you want to avoid this, and this gives rise to frustration. So the same thing you can do with charges. So let me just rewrite this interaction term here by subtracting the average density, which is 1/2, as I said before. It's just a constant shift of the energy. And you realize that you can go through the same argument here. You put one particle and one empty side here, and then one particle is 1 here, is positive. The empty one is negative, so you gain energy. You do the same here, but these have the same sign, so you pay an energy. So exactly the same thing happens with charge. The good news is that usually people who are interested in magnetic frustration, they treat localized spins, and here the charges can also move, so it adds a degree of freedom to the problem. So this is for a triangle. Now let's see what it gives when you go to a real lattice. So again, let me take this 1/4 filled example. So I'm on a square lattice. I add Coulomb interactions at least to nearest neighbors. What I get is this checkerboard order. I get this because in this way, all occupied sites here are surrounded by empty sites, and they pay no energy. So this state is insulating, so it has a gap. And it's twice degenerate because you can imagine shifting the whole pattern by one lattice site, and you have a second option to stabilize your charge order. Now you try to do the same on a triangular lattice. There is a trouble here because so you want to put one particle per two sides. So these bonds here are happy, but these are unhappy here because they are paying energy. And by the way, because this triangular lattice looks like a square lattice that is squeezed on the vertical direction, this is nothing but the checkerboard order that you have seen before. It's just squeezed, and then it looks like stripes. So the fact is that you have many more choices to do this, and any of these striped structures where each particle has two occupied neighbors has the same energy. And you can show that there is an infinite number of these. So now if you start plugging in thermal fluctuations on this, you get very interesting physics. Luke will speak about it tomorrow, I guess. What I'm interested in here is quantum fluctuations and how these can lead to some quite exotic state of matter. So this is what I'm showing on the next slide. So we have seen that we cannot satisfy all bonds on the triangular lattice. So every electron cannot be happy, but can we make them at least less unhappy? And to do this, we construct a charge-ordered state in the following way. So we have to put one particle per two sides. We start by putting all the particles that we can in order to avoid these unhappy bonds. And this makes 1 per 3 sides. But we have some particles left that we have to put in. And what we want to do is put them on these vacant sides here. And it's easy to realize that at the classical level, the electrostatic energy of this object is exactly the same as the one of the stripes. But because these electrons now live on this honeycomb lattice, they can move and they can gain kinetic energy by this motion. And so immediately, as soon as we plug quantum fluctuations, this state here gets a lower energy than the stripes. So this state is called a pinball liquid. These particles here are localized. They're called pins. And the balls are the particles that move on this honeycomb lattice. So this state has quite interesting properties. It's a charge-ordered metal with this threefold periodicity. And we have seen this morning that there are many people interested in non-Fermi liquid behavior and bad metallic behavior. Well, this gives us at least 2 routes to get this non-Fermi liquid behavior. So here is the phase diagram, temperature versus Coulomb interaction strength that is calculated for a single band electron extended Hubbard model on this triangular lattice. So there is this charge order line here. And what we see is that when we approach this line, there is a whole region of bad metal where the quasi-particles are destroyed. There are large resistivities, large mass enhancements. And this extends to very high temperatures. It's pretty much the same as what Vlad was showing today. This scale is half the transfer integral. It's probably 1,000 Kelvin. So this bad metallic region is very broad. There is a second route. So this is coming from the homogeneous metal. Now, once you're in the charge-ordered phase, remember that there are these electrons that are moving on these interstitials, but there are localized electrons that are there and act like pins in a pinball. And if you think of the spin, what will happen is that these local electrons have local moments, and then the itinerant electrons can be scattered by these localized moments, exactly the same as you get in heavy fermions, where you have these conduction electrons that are scattered by the fluctuations of the F electrons. So this was a kind of a general framework for what you can expect when you frustrate charge order. And now let's see if there are experimental realizations of all this. So all these studies of extended Hubbard model on quarter field systems started from these ET2 organic, two-dimensional organic conductors. So ET stands for this molecule here, BEDT TTF. These form layers. You can see this lattice as some deformed triangular lattice. Because these are pi orbitals connecting molecules, actually you can really efficiently describe the system with only a single band, because the other molecular orbitals are very far in energy. So you basically have a single band model on some anisotropic triangular lattice. Now, by construction, these systems are doped by 1 hole per 2 molecules. So it's exactly the case we are interested in. The bandwidths are quite narrow, so you can expect Coulomb interactions to be really important there. And in fact, charge-ordered phases are very often observed, but unfortunately, they have this striped shape. So the threefold pinball liquid is not observed in these systems. So if we really want to find this pinball phase, we have to go to other systems. So one idea is this decalcogenide family. There's one very interesting example, which is 1T-TAS2. It has charge order and some Mott physics. But here, the period of the unit cell is 13. So it does this David star-shaped objects. So it's probably related to these ideas, but it's not really a neat realization of this. There are many other systems with triangular lattices that you can think of, like cobalt oxides, but also you can imagine doping organic semiconductors with ionic liquid gating, putting adsorbates on surfaces, and or even in trap cold ions. But up to now, this pinball phase has not been seen. So this is the guy. So we became interested in this material a couple of years ago because, well, first of all, it has a triangular lattice. So this is silver nickel O2. It's the crystal structure is delaphosite. So you have these layers here. The nickel is in an octahedral environment. And when you see from above, these are the nickel ions. They form a triangular lattice. So if you look at the valence, on the average is 3+, which means that all the T2G, so there is this splitting that is due to the octahedral environment. All these levels here are filled, and you're left with 1 electron on this doublet here. So actually, this is very interesting because it's true that we have 1 electron per site, but we have the 2 spin states and the 2 orbital states. So effectively, this is also a quarter-filled system on a perfectly isotropic triangular system. So one could expect to see some physics related to this pinball. So what's the experimental situation then? Well, there have been X-ray and neutron scattering experiments that have observed exactly this threefold order. So what they see is that there are charge-rich nickels here, 1 every 3, that have a valence close to 2+. And then these are charge-poor, and on the average, they're more close to 3.5. So this is sketched here. You can recognize this triangular lattice of charge-rich sites, and then the honeycomb lattice of mobile carriers. So resistivity, so this is the transition occurs at 365 Kelvin, and it's actually a metal-to-metal transition. So you go down, so it's, let's say that according to the definition we saw this morning, this is a metal. It goes up with temperature. At lower temperature, it's also a metal, but you have this jump here by kind of 10%. Now, what is probably more interesting is the low temperature region. So forget about this magnetic ordering that occurs at very low temperatures. All this part here, you have a quadratic temperature dependence, then a crossover to something that looks linear and then bends down. The values here are in the milliohm centimeter range, that if you remember from this morning, this is a bad metal. More, well, you don't see here, but well, first of all, if you do fits to the susceptibility, you extract quite large values of the local moment. And trust me, there is a very slight change of slope here at the same temperature where there is an anomaly in the resistivity. The thermal power is also anomalous. It starts like a good Fermi liquid, and then it saturates and even changes sign. So this is really close to what is expected for correlated systems. And then optical conductivity, we know that this is the smoking gun. We learn a lot from here. Nobody has measured. So Martin, you know what you have to do. I think it would be really interesting to measure this and transfers of spectral weight. OK, to summarize the experiments, so this material here has charge ordering. Charge ordering is threefold. There are large local moments pointing to these localized pins. Resistivity and thermal power are anomalous. What I haven't shown is that the specific heat is also quite large. There are few measurements of RPES, but only on polycrystals, and there is no sign of quasiparticles, nothing, no weight at the Fermi energy. And this is compatible with some destruction of quasiparticles above this temperature T star. So is this a pinball liquid? We could just say, well, of course, but let's try to do some theory, which is what we have been doing this year. So we have to stretch a bit this theoretical description because it was initially devised for single band models, and here we are dealing with d electrons, so we have to plug in Hund's coupling. So this is just the extended Hubbard model I was treating before, and we add this Hund coupling that looks very complicated. I have put a picture here so that I can understand what's going on. So the main things here are these three potential energy terms. So you have two orbitals, and these represent the energy you pay when you put two electrons on the same site, either on the same orbital or on different orbitals, different spin orientations, or different orbitals and same spin orientation. So we know that Hund coupling will favor aligned spins, and this is indicated here because the energy cost is reduced with respect to the opposite spin alignment. So what do we expect now? We expect that because this Hund exchange energy is maximum when I put two electrons on the same site and they are aligned, so this will favor a state with these objects that look like spin ones, local. And so what we can expect, well, of course, it comes on the next slide, but what will come out is this. So there is a very broad region of the phase diagram where there is a charge ordering with these two electrons localized here on one site every 3 sites, and all the rest go flowing here as is observed in the experiments. How much time do I have? Good. So here is the phase diagram. We calculated by both some unrestricted Hartree-Fock approach, and then we confirmed by dynamical mean field theory. So this is the strength of local, the Hubbard term, so the local interaction U, and this is the ratio of Hund coupling to this U. And we have fixed a quite reasonable value of the nearest neighbor repulsion V so that we can get charge ordering. So when we start from up here, because we pay a lot of energy if we put two electrons on the same site, we don't want to do this, and the system is homogeneous. There is one electron per site. On the other end of the phase diagram down here, the cost in U is small. So what we want to do is put all electrons on the same site, as many as we can. So we will put 3 here, and on this site and this site, it will be empty. So this is full charge order. But there is this intermediate region here where you get exactly what I was showing before. So you get 2 electrons on this site and then the remaining electrons act as a liquid flowing in these interstitials. And you see that as long as you increase the Hund's coupling, this region here broadens and it stabilizes this pinball. So that's good news because also the range of microscopic parameters is quite reasonable for these materials. So with values of U over T slightly larger than 5 and reasonable Hund's couplings, you can really stabilize this phase that is observed. So two more slides. This is just illustrating the evolution of the sublattice densities when you do scans versus the value of U for constant values of Hund's coupling. So what you see, for example, in this red line here is somewhere at a value of 0.3 for the Hund's coupling. So you start from a fully ordered phase here where you have 3 electrons on one sublattice and 0 on the others. In this intermediate region, you're around 2, so 2 and 0.5, and then eventually you get to this homogeneous metal here where everything is homogeneous, equal to 1. So with the dynamic mean field theory, we can calculate the quasi-particle renormalization, which is this Z parameter. And what we see is that in the whole pinball region here, when you increase the Hund's coupling, you stabilize the pinball liquid, and this pinball has very strong correlations on these pin sites, which is indicated here. So the renormalization is like a factor of 10. So last thing we can calculate is the effective magnetic moment. So this is again a scan versus the strength of the Coulomb interaction, the local. So if you put no local interactions, the effective moment is 1. But then at some point you cross this boundary to the pinball liquid, and then it shoots up and actually reaches values of around 1.8, which is exactly the one that is measured in experiments. And OK, we did some calculations showing that there is an antiferromagnetic coupling between these local moments, and this explains why they order at low temperature. So to conclude, I hope that I showed you that when you combine Coulomb interactions and frustration, you can get a lot of very interesting physics. And one example is this silver-nickel oxide that contains all these ingredients here and shows many poorly understood phenomena, and we think that it's a neat experimental realization of this multiband pinball liquid. So we are now working on performing temperature-dependent, calculating temperature-dependent properties, and I think it's time to go back to do experiments like photoemission or optical conductivity. Thank you for your attention.